So hello, welcome to another day of example problems. Today we're going to look at example problems from chapter 28. Hopefully you got a chance to at least look at the problems I put up, but I'll go through the solutions. Now these in general are all going to be about interference, really. Maybe some polarization, but different types of interference. Interference when light goes through a double slit. Interference when light goes through a thin film. Interference when light goes through a single slit. Or a diffraction grating, which is just like a shit ton of slits, and then maybe a little bit of polarization. So I'm going to jump right in and say this first problem says monochromatic light falls on a screen 1.75 meters from two slits. Before I finish the sentence, this is a double slit. I know that because it says two slits. So for double slit, I have my equations up in, I have my equations for double slit in here. And I'll say, okay, the screen is 1.75 meters away. That's L. And the slits are separated by 2.1 millimeters. That means D, the distance between the slits, is 2.1 times 10 to the negative third meters, or 0.0021 meters. The first and second order bright fringes are separated by 0.552. That means the distance between the first and the second. The change y would be where the slit is, but we're saying there's a change in y of 0.552 times 10 to the negative third meters, or 0.000552 meters. And it says, what is the wavelength of the light? Well, they said this is the distance between the bright spots. And for bright, as I have up in that weird highlighted thing, although I'm going to switch to a smaller weird highlighter. Well, actually, just box it. For bright, I know this is the equation. That the y value for bright is lambda L over dm. Now, in this case, I didn't say what y is. I said the separation. But I say that's for the first order and the second order. That means the difference of m equals 1 and m equals 2. And so I can say delta y, the change in the two, is just going to be the value when m is 2 minus the value when m is 1. But if I factor this out, this is equal to yl over d 2 minus 1, which is just yl over d. That, yeah, they're all going to be equally spaced. And so the space between two slits would be the same as the space from the 0 to the 1. So I'm going to take this and just rearrange. Say if delta y equals lambda L over D, if I want to get lambda, I'll multiply both sides by D, and I got to see how much space I have. Okay, I'll multiply both sides by D, and I'll divide both sides by L. And I'll get the wavelength would be the distance between 0.000522 meters times the space between the slits, 0.0021 meters, over the distance away, 1.75 meters. And doing that math, I get 6.62 times 10 to the negative 7, which is the same as 662 nanometers. Focus. And so I say this has to have a wavelength of 662 nanometers, which is in the red pretty heavily. It's right about here on that wavelength. For the record, a helium neon laser, which is like the red lasers, like most common laser pointer red, that is 632. So this is a little darker red than that. But yeah, it's a nice dark red. Make sense? Any questions though? No. Okay. If I ask for bright or dark spots, you just use the dark equation instead. It's really always there. The second question says a thin film. Well, I'm going to stop right there and say, okay, this is a thin film problem. I know it's a thin film problem because it says the word thin film. These problems are usually pretty easy to figure out what type of problem. So either say double slit or Sigwood slit or diffraction grating or thin film. For thin films, though, the equation changes depending on the setup. And in this one, it says I have a thin film of glycerin. Of a thickness of 524 nanometers with air on both sides. And it says white light goes and hits it. When the white light hits it, what wavelengths in the visible range between 400 and 700, really visible is like 750, but whatever, between 400 and 700 are strongly reflected. See, what's going to happen is when light hits it, some will reflect, some will refract. But once it refracts to the other side, there again, some will reflect. And so I'm going to look at the change between what I'm calling ray 1 and 2 here. Now, I need to think of how many phase reversals they have. A phase reversal happens. Gotta make sure I don't do this backwards. This is one of the things that I always need to double check. Yep. We're only going to have one phase reversal here. We're only going to have one phase reversal because I'm going from a lower value to a higher value of n, going from here to here. But for the next bit, for the other one, I'm going from a higher value of n to a lower value of n. And so so that means I only have one phase reversal. So I'm going to take this chart that I put right over here, and I'm going to say there's only one phase reversal. There's only one phase reversal. I'm only going to use these equations. And I want what wavelengths will be strongly reflected. And so you know what? That means I only want the constructive piece. And I can say that we'll have constructive interference when 2nt equals m plus 1/2 lambda. Well, n will be the index of refraction of the middle piece. I'm not going to use 1. I'm only going to use 1.473. T will be the thickness, and m could be a whole bunch of values. Now what I'm going to do is I'm going to just rearrange this and say if I divide both sides by lambda, the wavelength is 2nt m plus 1/2. And I ask for what wavelengths in that range. I want to be honest, there's no quick, easy way to necessarily know what that is. I mean, I can plug in what numbers I know. 2, n is 1.473, t is 524 times 10 to the negative 9th meters, but I'm not sure what my m value is. And if I reduce this, which I did just to make my life easy, that's 1543.7 times 10 to the negative 9 meters over m plus 1/2. And I'm basically just going to guess and check. I'm going to say, okay, m equals 0. That's going to be this divided by 1/2. Which is going to give me, oh, sorry. M can't be 0. I'm going to say m equals 1. I misspoke. It can't be 0 for these. And if I divide it by 1 plus 1/2, that's 1029.14 nanometers, which is far infrared. If m equals 2, 1543.7 times 10 to the negative 9 meters over 2 plus 1/2. I do that, and I get 617.48 nanometers. And so that's within the range. 617 is a pretty good orange color. It's 617, I just said? Yeah, it's between orange and red. It's going to be somewhere in this region. And then I say, okay, if m equals 3, 1543.7 times 10 to the negative 9 meters over 3 plus 1/2. That'll give me 441. And I just dropped in the 10 to the 9th and just writing the numbers in nanometers because, 10 to the 9th. 441. 441 is a dark blue. And I could do it then for m equals 4. And I'm just going to tell you, when m equals 4, you get 343. It's out of the range. And so I can say, you know what? What I'll see is either a orangish red light or a dark blue light. Those are what will be constructive. And what you'll see is a weird color pattern. You'll probably see like a greenish light, really, because you'll be mixing those two wavelengths. But you'll see just those two wavelengths where other wavelengths would be canceled out. Any questions there?
Yeah, for this condition, why can't we say that m is 0?
M equals 0 just isn't an option for thin film. I guess m could be 0. Yeah, I don't know why I didn't do m equals 0. I just skipped it. But if m is 0, it's gonna be 3,000 nanometers. So
Yeah, so you'd have to try other stuff anyway.
I could have done 0. I didn't plug in 0 in the solution, but there's no reason why I didn't. So yeah, it's just too big. I didn't bother checking it because I knew it wasn't. Okay. Now, this packet of problems is kind of working my way through the chapter. So the next thing is going to be single slits. And I'll keep my colors around so I can keep saying what colors things are. I'm running out of pages of this notebook. This is my wife's old notebook where apparently she was drawing Final Fantasy characters. All right. A beam of monochromatic light is diffracted by a slit of width 0.6 millimeters. Okay, slit width in single slit. It says a slit, so it's a single slit. And the slit width is what we call A. If it's 0.6 millimeters, that means it's 0.0006 meters. Diffraction pattern forms on a wall 1.3 meters behind the slit. The width of the central maxima is 2 millimeters. Calculate the wavelength of the light. The width of the central maxima, what that is, and I'm going to make a different picture show up that I don't have. I didn't have prepared, and I normally would just draw it, but I'm being lazy. Why draw it when I can just do that? The width of the central, in the single slit, we have an equation for the dark, and we can figure out where each dark thing is. The width of the single slit is going to be the distance from your m equals +1 to your m equals -1, or vice versa. Because the width of your, did I say the width of the single slit? The width of the central maxima is just going to be the space from dark to dark. And so if I want to know, if I'm saying the width of the single slit, the width of the central maxima is 2 millimeters, that means y for m equals 1 minus y for m equals -1 is 2 millimeters. But the thing is, this is a symmetric setup. I could just as easily say that means if going from drawing, there we go. If I want to say going from here to here is 2 millimeters, I can just as easily say that means going from one of the sides to the middle is 1 millimeter. It will be halfway. If I know either side of the maxima, I can say the middle of the maxima. Basically, I'm going from diameter to radius is the fancy thing of what I'm doing. So I'm just going to say y for when m equals 1 is 1 millimeter. Does that make sense? I didn't have to do this step. I could have solved with this and just done both and subtracted, which is what I did in the first problem. I could have done that again, but I did that in the first problem. I thought I would just simplify this time. The problem is that single slit, we don't do the small angle approximation. We're going to have to work with angles. And so I need to convert this to an angle, keeping in mind that the tangent of theta is y over L. And rearranging, that means y over L, oops, let me try it again. Theta is the inverse tangent of y over L, or the inverse tangent of 0.001 over 1.3 meters. When I do that math, I get a tiny ass angle, 0.000769 degrees. And what that is that's going to be where my bulk is for m equals 1. That'll be where my first bulk fringe is. Oh, sorry, that's a lie. That's just y over L. That's before I take the inverse tangent. I read the wrong line. 0.04407 degrees. I'm sorry, I just read the wrong line. Now, if my goal is to find the wavelength, I can take that and say that's the angle the first bulk slit happens. But that first bulk slit, we can say that the sine of theta bulk is m lambda over a. And therefore, lambda is a sine of theta bulk over m. But I said this was the first one, so my m will be 1. And since my m is 1, that means it's just going to be a sine theta bulk. Or 0.0006 meters sine of 0.04407 degrees, which is 4.62 times 10 to the negative 7 meters, or 462 nanometers. Which I can say what color that is off the top of my head. 462 nanometers is what I have memorized. Open. 462 nanometers, unless I'm mistaken. Is this color? That does not show up well on that. It's my laser pointer. I'm near positive. Wow, that is really not showing up on any camera well. What if I do that? There we go. That's 460-ish. I'm pretty sure. I can double check with the thing underneath. Oh, sorry, that's 560. I was wrong. Nope, 460 is the light blue. This is 560. I had the numbers wrong. I used to do this like professionally when I was a spectroscopist. I think I've said that before. And so like I used to basically do color by wavelength pretty quick, because what my job was, what I did my research for in undergrad was working out wavelength of things and figuring it out. So I had to do a lot of lasers, and I'd see the color and have to know, I know what it is just how to practice, but it's been 10 years. But yeah, 462 is a bluish color. This is 560. And a red laser pointer is 660. Any questions there?
Nope.
Okay. Let's do another one. Okay, so let's just take a look at what we've done, right? So we did a double slit, we did a thin film, we did a single slit. It shouldn't be too surprising to say the next problem is going to be a diffraction grating. So the hydrogen spectrum has a red line at 656 nanometers and a dark blue or violet line at 434 nanometers. What is the angular separation of these two spectral lines if obtained with a 4,500 lines per centimeter diffraction grating for the first order? Okay, first off, if I tell you a 4,500 lines per centimeter, that is not D for a diffraction grating. The diffraction grating is the space between each slit. And if it has 4,500 lines per centimeter, D, the distance between, will be the inverse of that. Will be 1 divided by that number, which is 2.22 times 10 to the negative 4 centimeters, because this is how many centimeters for each line. I'm not going to work in centimeters though, so I'm going to say 2.22 times 10 to the negative 6 meters, just doing my conversion. Now, for a diffraction grating, d sine theta bright equals m lambda. This said first order. So first order means m equals 1. So I'm just going to ignore my m because m equals 1. And that means the sine of theta b equals lambda over d. And therefore the angle is lambda over d. Now I want to know the difference between angles, so I'll just say theta red equals lambda red over d, or 656 times 10 to the negative 6 meter. Oops, I didn't write my inverse sign. Sorry, I skipped something. When I got to the side, theta b equals the inverse sign of lambda over d. I just had to disappear. So 656 times 10 negative 9 meters over d, which was 2.22 times 10 to the negative 6 meters. And I can do that, take the inverse sine, 17.19 degrees. I'll then do theta blue or violet and say the inverse sine of theta blue over d, which is the inverse sine of 434 times 10 negative 9 meters over 2.22 times 10 negative 6 meters. Divide them, take the inverse sine, 11.27 degrees. And the difference in angle would just be me subtracting those two numbers. I mean, really, that's how I make these problems complicated. I'm like, do it twice and subtract. But the general idea will go like that. Side note, I don't know how many of you already started looking at the lab for next week, but it's a lot of this. Just like, here's a laser light through a single slit. Here's a laser light through a double slit. And then I just go crazy and put light through other things and have you look at it. Okay.
All right.
Oh, let's do the fifth one. I don't remember what it is. Oh, the fifth one is an equation I did not put up on the screen. It's not polarization, but I'll solve it anyways. I think I have enough space on the bottom of this page, which will hopefully, because it's the last page of my notebook, unless I start working on Moogles. So this last one says, suppose a 5 diameter telescope lens, or 5 diameter telescope was constructed on the moon, where the absence of atmospheric distortion will permit excellent viewing. If observations were made using 500 nanometer light, what minimum separation between two objects could be resolved on Mars? For looking at resolution, the minimum angle of resolution for a round aperture is 1.22 lambda over d. That means the angle I could do will be 1.22 times 500 nanometers over the diameter. So it's going to be 100 times 10 to the negative 9 or 122 times 10 to the negative 9 radians. I can do that without a calculator. It's exciting. That's the minimum angle. Now, I didn't ask for the minimum angle. I asked for the size. But what we can say is if you're looking at something and you want to know how big it is, that bigness, that's the arc length for the angle, where you're some radius away, where your radius away would be the distance. And we can always say that arc length is angle times radius, as long as you work in radians. And so the size of thing you can see would simply be 122 times 10 to the negative 9 rads, times our distance away. 8 times 10 to the 7th kilometers, or times 10 to the 10th meters. And you get 9760 meters, or 9.76 kilometers. And you get that you can't look at small things. This is why it took us so long to have high resolution pictures of planets. We needed to be closer to them to take pictures, which is kind of what we do now. We send satellites up and have them take pictures. Doesn't matter how good the telescope is, that's the minimum resolution due to the diffraction and interference of the light. That's chapter 28 in a nutshell. Oh, just cracked my back. Any questions about it in general?
No.
Hope I'm good.
Okay, well, I'm going to stop there then. Have a good weekend.